Well, it's 4:30. The witching hour. Ha 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 ha. So on project one, we messed up and you guys couldn't access it until Monday when you were supposed to be available on Friday. Would you like us to extend the due date so that you have the weekend that you got, screwed out of in some sense, okay? You've already got it done. We can give a bonus half point or point for turning it in early. So, anybody else? Would you like the extra time on the weekend without a penalty or not? You're done? Okay, we got one who would not complain about the weekend. I'll get a second one. Okay. So we're going to do it on project one. It's and penalty of 15% per day, prorated hourly. We'll start then at Sunday at 11:59 p.m. Just add 2 days to that, and then give a half point bonus for turning it in on Friday at 11:59 max. Okay, fantastic. Well. Okay, we worked on differentiation in the form of rise over run and not noted here as of linear approximation of a nonlinear function. If a function is differentiable at a point, it's continuous. And by the rule of logic that says if A implies B, then not B implies not A. If the function is discontinuous at x0, then it's differentiable? No, it's not differentiable, okay? One doesn't say differentiable at x0. The following table is pretty much all of the derivatives that one needs to memorize, because with that and the differentiation rules, that the derivative of a sum is the sum of the derivatives, the derivative of a product, it's not the product of the derivatives, but it's something close to that. With the quotient rule and the chain rule, you can then differentiate almost anything. And then we have our friend, the power rule. But when it comes to really interesting and challenging functions, you probably want to use symbolic tools, and whether that's in Julia or Wolfram Alpha Pro, or MATLAB has a really good symbolic toolbox now. Those are all really good options. Python has a fine symbolic toolbox as well. And what I like about using software tools like that, it's much easier to document what one has done. And if the problem changes because the specifications at your internship change, it's much easier to go through and redo it than to derive everything by hand. I thought, just as a warm-up, I'm going to show you a different way to get the derivatives of sine and cosine that I'm guessing you haven't seen. So just for fun. So this is called Euler's formula. E to the ix equals cosine of x plus I times sine of x. And so I square root of -1. Better definition, it's the symbol such that when you square it, you get -1. So kind of up to you. Most people kind of think about it as the square root of -1. Okay, so we know how to differentiate exponentials. Now, the imaginary number I is just a constant. You can go through the definition. E to the ix, and we'll do that. sort of. Boom. So this would be d by dx of cosine of x plus I d by dx sine of x. And so surprise by surprise, when you differentiate e to the ix, and you can grind through this if you want, the I is just a constant. So by the chain rule, it just comes down. So I e to the ix is equal to this. Now, if I take I and I multiply it by e to the ix, what do I get? I'm going to get an I times the cosine and an I squared times the sine, and I squared is minus 1. So this is minus sine of x plus I cosine of x. Well, the two real parts have to be equal. And then the two imaginary parts have to be equal. So the derivative of cosine x is minus sine of x, and the derivative of sine of x is cosine x. How about that? It's much easier than going through all of the trig double angle formulas and everything that you need to do it to derive it by scratch. But, okay, so really, to me, you know, all those rules for combining sines and cosines and things are just really painful. And what I always do is I just convert them into using Euler's formula, so I'm manipulating complex exponentials, and it just simplifies everything. So anyway, was that cute or what? Okay, so anyway, so that's sine and cosine. We could do log if you wanted. Tangent is sine over cosine, so you differentiate it with the quotient rule. And arctangent will come about a little bit later. Okay, so I thought we'd do one practice problem and then we'll get busy on something else. Let's just make sure we're super strong on these differentiation rules. So what if I give you f of x is cosine of x squared plus 1. What is f prime of x? Okay, so I'll give you 1 minute to just quickly do that calculation. Got it mentally? Wow, you guys are fast. Okay, so this is really a chain rule, right? So we differentiate the cosine function, and we just discovered that that's minus sine. With the chain rule, you plug the second function back in. And then we need to do x squared plus 1 prime. And so this part stays the same, and then the derivative of that is just 2x. Okay. Is that what everybody got? Yeah, not too hard. Very good. So I think we can move on then from differentiation. So we'll move on to start looking at applications of single variable derivatives. So from physics, we know that speed is the time rate of change of position. And acceleration is the time rate of change of speed. From project 1, you guys are doing the opposite of this, right? From project 1, you guys are recovering position from velocity. And in a similar way, you're recovering velocity from acceleration. And I'm just using tau as some dummy variable in the integral. I could have put a y in there. I could put z, could put all sorts of strange things, but tau sort of looks like time, and so we're using it as a substitute for time. And that's because we've got time up here, so we don't want time down here as well. So what we see from here is that it looks like differentiation is the inverse of integration, and integration undoes differentiation. So certainly looks like differentiation and integration are inverse operations, one of the other. Okay, you guys have all had Math 116. You've seen the fundamental theorem, fundamental theorems of calculus, and so in Chapter 7, we'll explore this deeply. You know, because it could just be something that happens with physics type problems, but it's not. It's much more deeply ingrained into the very fabric of calculus. And I think when people understood that, they were a little bit surprised. But taking slopes and calculating area, one undoes the other. You know, in theory, in theory, it all works out, but in just looking at it, it's kind of non-intuitive that would be true. Okay. So in Chapter 1 on the pre-calculus, one of the important things is whether functions have inverses or not. Okay? And so I'm going to attempt to draw y equals x cubed. Okay. And then I'm going to draw another function that is a little bit different. I don't know, I'll just take a function, goes up, it rides along this curve, and then it goes up. So this function we call strictly increasing. Because if we have x1, x2, f of x, x2 bigger than x1 implies f of x2 is strictly bigger than f of x1. And this function is called non-decreasing. And here, x2 greater than or equal to x1 implies f of x2 is greater than or equal to x1. So we do not have strict inequality here. So this one is strict. And even if x2 is bigger than x1, it still can be the case that f of x2, for example, equals f of x1. So it's greater than or equal to. This function passes the horizontal line test. Remember that for checking whether scalar valued functions have inverses. This one, I deliberately drew it so it doesn't satisfy the horizontal line test, okay? It satisfies the vertical line test. It is a function, okay? And so you've got nice tests with derivatives. If the derivative of the function is strictly greater than 0, for all x in some interval AB, that implies f is strictly increasing. Whereas here, df by dx is greater than or equal to 0. For all x, an element of AB implies f is non-decreasing. Okay, so it never decreases, but it's not necessarily always increasing. Okay. Now, what is the derivative of x cubed at the origin here? Is 0, so is the derivative then strictly greater than 0? No, okay. Yet this function is strictly increasing, right? So it's not satisfying this condition. So see the textbook. So if df by dx is strictly greater than 0, except for a finite number of points in any, well, I'll just write it. Then f of x is strictly increasing. Okay, so the easiest test is you just look at the derivative. If it's always positive, then the function is increasing. If it's strictly negative, it's always strictly decreasing. If the derivative does not change signs, that's what dx greater or equal to 0, then you get the non-decreasing or the non-increasing criteria. But if you only violate this condition at a small number of points, so like here we only violate it at 1 point, okay, then it is still strictly increasing. So, okay, so that's one particular use of derivatives. And so if a function is strictly increasing, then on its domain, and on its range, it has an inverse. So for all points in the range of the function, there is an inverse. So that's pretty cool. L'Hopital's rule. Okay, so it's a means of finding limits for our indeterminate forms. Zero over 0 and plus minus infinity over plus minus infinity. Okay, so we have some really bad ones like infinity minus infinity, 0 times infinity. So we're not dealing with all of the indeterminate forms. We're dealing with 2 of them, 0 over 0 and infinity over infinity. Okay, so we want to understand limits there. Now, where does the idea come from? So suppose we have 2 functions that vanish at a point x0. And if we look at their linearizations at that point, assuming they are differentiable, okay? Oops, come on. Zero, 0. Okay, and those approximations become better and better as we get closer and closer to x0. So then the limit x goes to x0 of f of x over g of x should be the same as the limit x goes to x0 of f prime of x0 okay. Those two things cancel. And so it should equal f prime of x0 over g prime of x0. And that should work as long as the denominator is not 0, right? If the denominator is 0, then we're back potentially in this form if the numerator were to vanish, etc. Okay, so, but that's where the idea comes from. So L'Hopital's rule itself extends this. And it extends it to cases where maybe the derivatives do not necessarily exist at x0. Okay, so it's a little more general than what we just did, but it's the same idea. Okay, so we'll present that in just a second. So remember this guy Bernoulli who was part of inventing Euler's number? So L'Hopital was a student of his brother. So Bernoulli was the PhD advisor of L'Hopital. L'Hopital did not invent L'Hopital's rule. His PhD advisor invented it. And back in the day, mathematicians would sell results to one another so that they could somebody else could be famous and have social standing by having their name associated with this result. So to this day, it's called L'Hopital's rule, and he bought it off of his PhD advisor. Now, if I had ever attempted to sell a result to one of my students, I'd be out on the street, okay? But back in the day, things were a little bit different. So yeah, you may want to read about that in the textbook. I have the Secrets of the Arcane that you may have noticed. They're in these kind of bright pink boxes in the thing, and it's just strange facts associated with math, okay, and some of the people in math. And I don't know, when I learned that, I was just like floored, okay, that you could actually purchase a result from your thesis advisor. But that would be a great way to get a degree. Hey, can I just buy my PhD? You know? But anyway, so let's state L'Hopital's rule carefully, and then find cases where it's applicable and where it's not applicable. So this is L'Hopital's rule. This circumflex, it means that in older French, this was spelled Hospital, hospital. Okay, that's what that circumflex means. So in English, we have hotels, which in French has the circumflex in it, and we have hostels, which are like youth hostels. Okay, so we have both forms of the word. So pick some word that you don't want to write the S on, start putting circumflexes in it, and drive your friends crazy, okay? That's all it means, okay? Well, the circumflex, so. So let I be an open interval. X0 in I. And we have two functions. F takes I to R, and G takes I to R. That are differentiable on I, except possibly at x0. Okay, so the functions are differentiable on I, except maybe at x0, the derivative doesn't exist. But that's what limits are all about, okay? So limits are for straightening out cases like sine of x over x. When x is 0, how do you define that function? So electrical engineers use it all the time. They call it the sinc function. Okay, this is what limits are for. So if f and g satisfy, and there's three conditions. One, for all x in I, x not equal to x0, g prime is not equal to 0. So that's going to be the function in the denominator. Okay, so when we're doing L'Hopital, something like L'Hopital, we don't want to be dividing by 0, okay? Now, we don't have, the function may not be differentiable at x0, so this condition where here, I just plugged in the linearization at a point, so these derivatives had to exist to do the linearization about x0. Here, I would have had to have g prime of x0 existing and not being equal to 0. So in the more general L'Hopital's rule, the function in the bottom, its derivative should not vanish, but we don't have any condition at the point x0 itself. Two, we're in these indeterminate form of 0 over 0 or infinity over infinity. So the limit of x approaches x0 of f of x equals the limit x approaches x0 of g of x equals 0, or those two limits are plus or minus infinity. And so we can write it like this. Limit x approaches x0 of f of x, its absolute value is the limit x approaches x0 of g of x, its x value equals infinity. Okay, so that's just saying those two functions have limits, and they can be plus or minus infinity. So that's the other indeterminate form. And then the final condition is the limit as x approaches x0 of f prime of x over g prime of x exists. Let me put that in red since it's important. Okay. Can be finite or unbounded, but it has to exist. Okay, so it can't be like sine of x or sine of 1 over x. Okay, those limits don't exist, but if f prime is x squared and g prime of x is x to the fourth, that's fine, okay? Each of them are in infinity, but we can still take their ratio and evaluate what's going on. Whoops. Then we get L'Hopital's rule. Limit as x goes to x0 of f of x over g of x Okay, so that's kind of a gold mine for evaluating derivatives. And if you want even a little bit more, maybe this function on the right is an indeterminate form. If the second derivative exists, you can then extend L'Hopital's rule and apply the second derivative, the third derivative, etc. Okay, so questions on the import? All of the intuition, I think, comes from just looking at the local linearization about a point, okay? Okay, so let's do this one first. Limit x goes to 0, sine of x over x. Okay, so it's 0 over 0, so it's one of our indeterminate forms. So that's good. Okay, so we got 0 over 0, not infinity over infinity, fine. Does the derivative of the bottom thing exist and is non-zero? Yep, derivative of x is 1, so that satisfies that. And then does this limit ratio exist? Well, we don't know. We have to check that. So that's equal to the limit as x goes to 0. Derivative of sine is cosine of x. Derivative of x is 1. And so, yep, both that limit exists and it's equal to 1. So we're good. And so all conditions for L'Hopital are met. How about this one? Oh, excuse me, infinity. I knew I had something wrong there. Okay, so if we're viewing this as f of x and this is g of x, this is going to infinity, but this is going to 0, and that's not the standard L'Hopital's rule. So L'Hopital needs 0 over 0 or infinity over infinity. So it's not 0 over 0 or okay. Now we know from our previous work that exponentials dominate, and this thing is going to 0, and we don't care about the monomial, so we know the limit is 0. So how do you get that out of L'Hopital? Is you rewrite this as x over e to the x, and now it's infinity over infinity. So it's one of the indeterminate forms. So now it's legit to apply L'Hopital's rule. And so we do the derivative of x is 1, the derivative of e to the x is e to the x, and then it's 0, just like we knew it should be. I had one more. Where'd it go? Let's look at this one. What's the limit? This one is also x goes to infinity of x log 1 over x. Can you apply L'Hopital's rule to this, okay? So if this is f, that's going to infinity. As x goes to infinity, 1 over x goes to 0 from the right. And so the log function does what as you head to 0? It's going to minus infinity, okay? So infinity times infinity is not one of the indeterminate forms, right? So this is infinity times minus infinity. So it's not an allowed indeterminate form for L'Hopital. So this is the thing. We have these nice, cute theorems, but we do need to check the conditions under which they're being applied, okay? Now, we don't need to do L'Hopital's rule because this is getting, excuse me, where's my little laser thing? This is getting very large. This is getting large in the negative direction. So the product is going to minus infinity, okay? In the book, I go through and I apply L'Hopital's rule, pretending that I haven't, observed that it is not applicable. So if you try to apply L'Hopital's rule, you get the answer is plus infinity. Now that's about as big of an error as you can possibly have. It's minus infinity is the correct answer. You misapply L'Hopital's rule and you compute the answer as plus infinity. You are off by a lot, okay? So this is just, it's only there to highlight that it really is important to check the conditions, okay? Now, needs a better clip here, but that's not my problem right now. Here's a problem that Professor Nima Fazeli posed to the graduate students. And they struggled, okay? We want to compute the limit as x goes to infinity of the quantity square root of x squared plus x minus x. And I'm trying to draw to do this very clearly so that that minus x is not under the radical. Okay, so we'll take our break. I'm stopping 3 minutes early, but we'll still reconvene at 5:25. Stretch your legs, stretch your brain. See if you can compute this limit that the grad student struggled with, okay? But you are on break, okay? You can go up, walk around. You can get one of Max's very nice treats. He didn't bring pizza, but he's got everything else. So let's just think about this qualitatively. And it's going to give us the wrong answer, okay? But let's just think about it. I mean, we understand how limits go. X squared, you know, when x is like 1,000, 1,000 squared is so much bigger than 1,000 that x squared dominates x to the point where you're tempted to just say x squared plus x equals x. Because if you're doing a plot, you couldn't tell the difference after that, okay? And so if you eliminate this, the square root of x squared is x. And so you're thinking, this is approximately x, this is x, so the limit looks like it could be 0. And if somebody just made that argument to you, and you're doing something else, and then you've got to use it, you just go, yeah, that's fine. Okay. Okay, so you can go through it on your own, but the true answer is 1/2. Okay, it's not 0. The true answer is 1/2. Did you get it? Excellent. Anybody else? Oh, excellent. We have several people got us. You guys are grad school material, okay? So definitely grad school material. So it's limits 1/2. And just a little bit of nice factorization. And if you're interested, you can come back here and check it out. Okay, so put down your pens and pencils, etc. And I know that everybody online and in the room has seen Taylor's theorem before, but I'm still teaching to those who haven't. And I think when you see it this way, if you had any troubles with it before, they will all go away. So the whole idea of Taylor's theorem and Maclaurin's theorem is to approximate nonlinear functions with polynomials. So Taylor polynomials, finite, Taylor series, infinite. So how do they work? So when we're dealing with monomials, we know how to do the derivative. The n comes down, and then we go n minus 1. So that's how we differentiate monomials. But if you normalize them a little bit differently and write the monomial as x to the n divided by n factorial, then when you differentiate it, the n comes down, you get the n minus 1, and this constant just comes out, so you have n over n factorial. And n over n factorial, you just write it out, the n's cancel, and so this becomes x to the n minus 1 over n minus 1 factorial. And then you take the second derivative, and you get n minus 2 over n minus 2 factorial. And the third derivative, n minus 3 over n minus 3 factorial. So it makes it very consistent and clean to write monomials that way. Any problems with that? Okay, so let's just look at this polynomial where I put coefficients in the front, and I write, instead of just x cubed, I write as x to the n over n factorial. How do these coefficients relate to the derivative and values of the function, for example, at the origin? Well, if I just plug in 0 for x, this goes away, this goes away, this goes away, and I have a0. So fine. The value of the polynomial at the origin is the 0th or lowest order term in the polynomial. Cool. Well, let's calculate the first derivative. We went through the pattern. We'll keep a3, then this will become x squared over 2 factorial. We'll keep the a2, this will become x1 over 1 factorial. We'll keep the a1, this becomes x to the 0 over 0 factorial, so it's 1, and the constant goes away. So we get this formula. And then we evaluate at the origin, this goes away, and we get a1. So a0 is the polynomial at the origin, a1 is the first derivative evaluated at the origin, and the pattern continues. We differentiate this, the 2 cancels with this, we just get x over 1 factorial. This is just x, and so we just get a2, this goes away. We evaluate at 0, this goes away, and we get a2. And same for the third derivative. The fourth derivative is going to be 0 because this is a constant, but okay? So that's how that goes. So if we substitute all this back in, any polynomial can be expressed as p of x is this is a cubic, its third derivative times x cubed over 3 factorial, its second derivative at the origin times x squared over 2 factorial, first derivative times x over 1 factorial, and the value of the function, the 0th derivative. Okay, so that's just how polynomials work. And it's just taking these formulas, plugging them in for a1, a2, a3, a0, and using the prime notation here. Questions on that part? Works? Everybody's good? Okay. Okay, so what Taylor and McLaurin did is they just took this observation and said, if I want to approximate a function with a polynomial, I can use knowledge of its derivatives in such a way that I want to match the derivatives of the polynomial with the derivatives of the function at a given point. And when I take that given point to be the origin, that's called the Maclaurin expansion, which was actually done after Taylor's expansion, but it was hard to get work always circulated well. So Maclaurin just looked at the origin for his expansions, and Taylor took a general point. Fine, he just shifted the function, so f of x, and it's still true that the first derivative of f of x evaluated at x0, this constant goes away, you have this derivative is 1, all those things vanish, etc. So the left-hand side and the right-hand side, the derivatives are matched up to a desired degree of the polynomial, and then about a point. And that's what a Taylor expansion is. So they all just come from this fact here, that you can take polynomials, and we did the origin. If we had x0, this would be x minus x0 cubed, x0, x minus x0 squared, x0, x minus x0, and then x0. And it's all just this simple calculation. And then once you have that, okay, we already discussed how this ties in with L'Hopital's rule. So this is just using the first order expansion. But if the first derivatives vanish, you stick in the Taylor expansions, these two terms cancel, and you're left with this. The Taylor expansion is assuming that these derivatives exist at the point x0, and L'Hopital's rule says, well, this derivative doesn't have to exist at x0, but it can't vanish around x0, and then the limit of these two ratios, if I plug in x, and this should be x0, do it. So L'Hopital's rule is really the generalization of applying Taylor's theorem or Maclaurin expansions to doing it. So just a tiny bit more sophisticated. Make sense? A lot of sense? Too much sense? Not enough sense? Okay, so when it comes to Taylor series, some people come away from their Calc 1 course thinking that Taylor series are the coolest application of derivatives that they ever see in the course. And if you feel that way, I don't blame you. I may have had that impression myself because I was just taught the standard mathematics way of thinking. But here's the thing. In real engineering, 98, it could even be 99 of your Taylor expansions that you compute, they will be first order. Okay, you stop there. You almost never use the second order Taylor expansion. A few tiny examples when you're checking local minima of functions, you might use the second, almost never the third then. Okay. The interesting exceptions are when the function is infinitely differentiable. And what that means is you can calculate the nth derivative for all n bigger than or equal to 1. And any polynomial is infinitely differentiable because if you differentiate up to the highest degree, you get a constant, okay, and then the next one is 0, and all derivatives after that are 0. But there are interesting functions that have infinite number of derivatives. And the easiest is the exponential, because the derivative of the exponential is the exponential. And then if you just keep calculating derivatives of that, you just get the exponential back. So it's infinitely differentiable. And sine and cosine have the same thing because derivative of sine is cosine. The derivative of cosine is minus sine. So you do another derivative and you get minus cosine. And then you differentiate again and you get plus sine back and it just circles. So sine and cosine are infinitely differentiable. And when functions are infinitely differentiable, you can think of representing them not as just a finite polynomial, but you use all of the information in the derivatives. And this is called a Taylor series. And the word series is because we're adding up an infinite number of terms. So there are zillions of functions for which those things exist, but there's only 3 of them that you'll see very much as engineers. And so those are the ones I want to point out. Okay? So the exponential function, this is its Maclaurin expansion. This coefficient should be the first derivative evaluated at the origin, and e to the 0 is 1. Excuse me, the value of the function at the origin. This coefficient of x is the first derivative at the origin, but that's just e to the x at 0, which is 1. The coefficient in front of x squared over 2 factorial is the second derivative of e to the x evaluated at the origin, which is once again 1, etc. So all the coefficients in the Taylor expansion are just 1. And here we're taking x0 as the origin. So it's 1, 1, 1, 1, etc. All of these are 1. Okay, so this one is worth memorizing for sure. Definitely memorize this one. And it's simple because it's 1 plus x, etc., and the general term is just the sum of x to the k over k factorial. X to the k over k factorial. So that's the exponential function. Sine and cosine, because of this pattern, when you evaluate at the origin, you get 0, 1, 0, minus 1. Here, you get 1, 0, minus 1, 0, and then that repeats. Okay, so it just cycles through 1, minus 1, and 0. Whereas the exponential, it's all 1. So sine has all the odd terms, and most people don't have it memorized. Okay, I always look it up, even though it's not hard to derive, right? So it goes plus, minus, plus, minus, plus, minus, because of sine. Derivative sine is cosine, but the derivative cosine is minus sine, so that's why the alternating signs. Okay, and I don't know anybody who memorizes this, okay? Maybe some of you will, but not me. So it has odd terms, and the cosine has all the even terms. Okay, and once again, okay? And the signs plus, minus, plus, minus, plus, minus is because of the derivative of sine and cosine at the origin, alternating in sign at the origin. Okay, so this Euler's formula that we got, come on. Okay, so if I plug in Ix for x, so this is Ix, x squared is I squared x squared, and I squared is minus 1. Ix cubed is I times I squared, so it's minus I times x cubed. And then x to the fourth is going to be I to the fourth, which is minus 1 squared, which is 1. So if you go through here and put in Ix, you're going to get an I here, an imaginary term here. You're going to get a real term here. All the odd terms will give you an imaginary thing, and all the even terms will give you a real coefficient. And so when you plug all that in, what happened here? When you plug all that in, you get e to the ix is, here's the even stuff. Where does the minus sign come from? X squared. When you plug in ix here, you get I squared. There's the minus, and then you have the x squared. And then x to the fourth, it's plus because you have I to the fourth, which is I squared squared minus 1 squared plus 1. Okay. And et cetera. So that's where, oh, I see I messed this up. Can I get it to go back? Yeah, awesome. Okay, so that's where Euler's formula comes from. One way to do it, okay, is you simply take the Taylor expansion for e to the x, you plug in ix, and when you match up all the terms, you get the Taylor series for the cosine with the even parts of x, and you get I times the Taylor series for sine of x. And that's where Euler's formula comes from. What do you think? Cool? Not cool? Interesting? Okay, now I want to blow your mind, so open your mind so it can be blown. Okay. What are other objects that we can compute powers of? Squares, cubed, fourth powers, things like that. What other objects besides just scalars? Anybody online have an idea of something a little bit different than just a number that you can square? A vector? That's not bad. With the dot product, it's sort of like squaring it. So I'm going to generalize your answer, Jason, and say an array. Okay, but what kind of array, when you multiply it times itself, you get an array of the same size back? A square matrix. Okay? And when you cube it, you get the square matrix back again of the same size. Huh. Whoops. Go back to wherever you are. So, let's think about 1 here in a little bit more abstract way. So 1 is the multiplicative unit in the reals. 1 times x is x for all x's. It's the multiplicative unit. That's the name for it. If I were doing n by n matrices, what is the multiplicative unit? The thing I can multiply any n by n matrix by and I don't change the matrix. What is that called? Identity matrix. Yeah. So, this is something we're going to do when we start solving differential equations. It's going to become really important. So this is just looking ahead because it's awesome. Let A be n by n matrix. So then A squared, A times A. That's still an n by n matrix. And in general, A to the k, which is A times A to the k minus 1 by induction, n by n matrix. And then A to the 0, we're just going to define that to be the n identity matrix. And then this is totally rad. I can define the exponential of a matrix as in plus a. I'm just going to go to the, so this would be over 1 factorial, a squared over 2 factorial, a cubed over 3 factorial, dot, dot, dot. Okay, so essentially anything for which you can calculate a Taylor series. Here we're using the Maclaurin series. We're at the origin. So what? Okay, do the Maclaurin series, even though nobody calls it that. They always call it the Taylor series at the origin. I could take the expression for sine and calculate this thing as well and define sine of a matrix. And it's not sine of the entries, okay? And we will discover that. But this object turns out to be crucial in the solution of systems of linear differential equations. Hey. So I know all of you are in here with bated breath waiting for us to get to differential equations. And I just wanted to let you know that one of the tools we're going to use is going to Taylor's expansion for the matrix exponential, interpreting it in a slightly broader context where 1 is the multiplicative unit in the reals. We replace it with the multiplicative unit in n by n matrices, and then we can define the exponential of a matrix, which seems totally weird, okay? But it actually gives you the solution. When you put AT and you put T's in here, it gives you the solution to linear differential equations in a really awesomely powerful way. How about that? Okay, question, yes? Can you say it a little bit louder for me?
What does mean in the context of power matrix?
So what is it? Can you hear this, Max, and tell them what's the question?
Oh, can you repeat that one? What does it mean to have a matrix as a number's power? As an inverse, like e power a, where a is a matrix.
So I think I get the gist. So are you used to this as a nice function of time?
Yeah.
It will turn out that it's the solution of this differential equation. X dot of t is a times x. X at 0 equals 1. E to the at is going to be the solution when x is an n vector, a is a matrix, and x at 0 is the identity. So the interpretation of it is it gives you the complete solution of the differential equation. So if you've heard of a mass spring damper before where it oscillates and dies out, that's a linear system. You can write its solution as a matrix exponential. So that's where it's going to happen, yeah.
If you raise like a scalar number like e to a matrix, what does that do? What does that mean?
Yeah, so this is where mathematics is powerful. So remember, we got to x to power y by replacing y with a rational number okay? And we could build it as multiplications and roots, okay? And then we got it concrete, and we took that rational number as a better and better and better approximation of the exponent. And that's how we defined x to the power y. And e to the power x is defined in the same way. It's that process. It's a limiting process, okay? This is totally different. I don't have a scalar with an a to the power. This is notation for taking this Taylor series and then interpreting it on a broader class of elements. And we will compute them when we get to it, but I guess I'm just trying to leave you with something that you might want to go, ooh, ah, because it's totally mind-boggling to think about taking a scalar and raising it to a matrix if you think about raising things as the same way that we defined x to power y. It is not that at all. It's taking e to power x, applying calculus and realizing that it has a power series expansion, and then realizing that power series, even though we do them for real numbers, we can also do them for n by n matrices simply because a matrix to a power, an integer power, is still a matrix of the same size, so we can add them up, okay? So this is calculus full blown. You can't get to that answer by thinking about replacing a with a rational number and then doing it. It doesn't work, okay? It's really calculus. And so this is just notation that is evocative so that you think about e to the x in this way as the power series. That's what it is. It's simply notation. Yeah. So I think I have intrigued you, and that's all I wanted to do at this point. So it's going to be another month or so before we do this for real in class, but it's going to be fun. It's just totally different than anything you will have done before, is my guess. So it's really calculus writ large. Calculus on matrices in some sense, okay? Cool. We've got some time, so let's start working on partial derivatives. And we'll do this in Julia on Monday so that you see that the calculations that are involved here are extremely tedious by hand, but with the right software tools, it's not a problem at all. So partial derivative. So what is a partial derivative? I know what a full derivative is, but what is a partial derivative? So are partial derivatives, I assume they're not covered in Math 115, is this correct? Correct, okay. So consider, they weren't covered in my equivalent of that. Okay, so let's take a function that depends on two variables, but it just returns a scalar, okay? So finally, we're doing things that you guys haven't seen before. It's going to be a simple function that's built, let me just write it x1, x2. You guys don't need the multiplication sign. And then I'll make sure it looks like x2 squared by writing it like that. Okay, so it's a function of two variables, x1 and x2. Partial derivative of f with respect to to x1 is, and this is the notation, it's a funny, so we change from the standard Latin D to this symbol called partial. Derivatives of functions are functions, and partial derivatives of functions are functions as well. It still depends on x1 and x2, and we'll define this symbol in a second. But this is what it is. It's a limit. Just like we define all derivatives, limit is h goes to 0 of f of, and let me just try to highlight where the okay, so I'll write this out, but let's just think about it. So notice what's varying here. H is what's varying, and it's only varying the first variable. X2 is remaining constant. Okay, so this is just like f of x plus h minus f of x over h, except now x is a vector or an array with multiple elements in it, so it's a multivariable function. And I'm varying only the first component here. First component is said here. We only do this. Okay? So in other words, we hold x2 constant and differentiate f with respect to x1. Okay. Now, I can define a partial derivative with respect to x2, and we will do that in a second, okay? So it's the derivative of f with respect to the first component when you freeze x2. So this symbol is called partial. If anybody here likes LaTeX, it's backslash nabla. Oh no, excuse me, it's backslash partial. It's the gradient that's nabla. Okay, backslash partial. So just partial. So they wanted to create a symbol so that you understood it's not the ordinary derivative, it's a partial derivative. Partial because we're only differentiating part of the function, the part that depends upon x1, leaving x2 as a constant, okay? And then as you might guess, partial with respect to x2 is by definition equal to limit, and I'll highlight the h. x1 is kept constant. I calculate the rise with respect to x2, so it's still rise over run, just like the normal derivative. Okay, so we hold x1 constant. Compute the slope, and I'll write with respect to is WRT with respect to x2. Okay, so that's what partials derivatives are about. Okay, so let's see if we can compute our first partial derivative. Let's take f of x1, x2, once again, same function we had, x1 times x2 plus x2 squared. Okay, and let's evaluate its partial derivative with respect to x1. Okay, so let's just do it orally, then we'll write it down, and then we'll write it down again, okay? So, but once you see what's going on, it's just like the ordinary derivative, but it just takes getting used to. What is the derivative of x1 with respect to x1? It's just 1. Now, when x2 is a constant, what is the derivative of this with respect to x1? It's the answer that you think it is, because x2 is a constant. The derivative of a constant times x is just the constant. So it's x2, okay? And if x2 is being held constant, we're going to write all this down. What's the derivative of a constant squared? 0, okay? So this equals 1 plus 0 plus 0, which equals 1, because I'm going to write it all out, and then a week from now you look at these notes and he goes, what is he doing, treating us like children? Okay, that's what you'll be thinking, but not right now. Okay, the partial derivative of x1 is 1. The partial derivative of x2 with respect to x1 is 0. The partial derivative of x2 squared with respect to x1 equals 0. So x2 treated as a constant. So that's what partial differentiation is. We take derivatives with respect to one variable at a time. It's just slopes, just like we did before. But if we have a bunch of variables, we hold all but one of them constant, and we do rise over run with respect to the variable of interest. Question? Yeah, I'm just not hearing you. It's like an echo.
Shouldn't it be 1 plus x2 is 0?
1 plus x2 is 0. Because x2 is a coefficient.
Oh, x2, yeah. So this is x2. Yep. I should read my own notes. No, wait a minute. Yeah, because this is x1, x2. Yes. Yeah. Thank you for pointing that out. That was embarrassing. And the x2 is because this is a constant times x1 the x2 comes down. Okay, let's see if we can do the other one more quickly. df by dx2 of x1, x2, and let me help you out by putting f of x1 on the screen. So it's x1, x1, x2, plus x2 squared, okay? So now we're holding x1 constant. When we differentiate this term, we get this time 0. We're holding x1 constant when we differentiate with respect to x2. So I'm not going to get it wrong this time. I said it right, but I wrote it wrong. We get x1. And then when we differentiate x2 squared with respect to x2, we get our usual derivative of monomial, 2x2. Okay, so this equals 0 plus x1 plus 2x2 and once again, because d by dx2 of x1 is 0. x1 is held constant. d by dx2 of x2 is just the usual derivative. It's 1. And d by dx2 of x2 squared, we know how to differentiate a monomial. We get 2x2. Okay, we'll do one more, and then we're just gonna, we'll call it quits. It's just, I'll give you a problem. Okay, so now here's h of x1, x2 equals cosine of x1 times x2 squared. So I'll put a square bracket for the argument of the cosine. Now, all of the rules of normal differentiation apply. The chain rule, the quotient rule, the product rule, the power rules, all of them are the same because you freeze n-1 variables and differentiate with respect to a single variable at a time. So it's just, they're just single variable derivatives, but it's weird to treat x2 as a constant sometimes when you're differentiating with respect to x1, et cetera. So you guys calculate that one, and then we'll do it, and then we'll go home and see how much snow is out there. Is there much snow out there, Devin, when you came in? Ah, there was no snow on the 3rd floor, huh? I won't say that. Okay. So, okay, so compute dh dx1 and then compute dh dx2. Okay, so we're ending the lectures on high notes, 2 new concepts. Exponential of a matrix, oh, mind blown. And now derivatives of variables that are sometimes 0, sometimes not, depending upon what derivative we are computing. You got it? You guys online, you got an answer so that when you compare it, you've got something going? You guys got it over there? You think you've got it? Come on.
James says no snow yet.
No snow yet, huh? Okay. So we apply the chain rule. We first need to differentiate cosine. What is the derivative of cosine? Negative sign, yeah? Okay, so we got minus sine and then we need to differentiate with respect to x1, x2 squared. Now, I never write this out like this when I'm really doing them, and you won't either very soon, okay? But we're just applying the chain rule here. And then the partial derivative of x1, when you have x1 times x2 squared is a constant, so this becomes x2 squared. Awesome, isn't it? Second one, it's the same process. Derivative of cosine minus sine, and just trying to be very clear with my bad handwriting that, okay, we plug the argument back into it. So this is f composed with g, it's f prime at g. That's what we have here. And then times partial derivative with respect to x2 of x1 times x2 squared. And x1 is a constant, x2 is a variable. So this becomes minus sine x1, x2 squared. x1 is a constant, so we have x1, and then we differentiate x2 squared and get 2x2. So clearly this we would more naturally write as 2x1, x2. Is that what you got? Wow, you guys are good. And we don't want to end on a bad note, so let's end right there, okay? And we'll pick up with partial derivatives, but this is going to lead us to gradients and Jacobians. Gradients is gradient descent, which is how neural networks are trained, okay? And Jacobians are all over robotics, and we use them for taking complex nonlinear functions and replacing them with a linear approximation, and that'll give us a matrix times something. That's how a vector linear equation looks like ax plus b. We'll write it as b plus ax, where b is the function at a point, and the a is the Jacobian, and the x is x minus x0. So it's going to lead us to some really cool stuff. So anyway, thank you. Sounds like everybody gets to walk home, drive home, take the bus, and no panic. There were people calling for the university to be closed today because of the threat of snow. And wow, we got through the whole day. We'll see how it is tomorrow when we get up. But anyway, we don't have to come here tomorrow. We'll see you guys Monday.